Hello everyone, this is Dr. Lennon, and today we're going to talk about exponential functions. So exponential functions are very different in nature from the polynomial functions that we've discussed previously. So let's just start with the definition. The main way to think about these is they exhibit a pattern that is multiplicative in nature with respect to the output variable. So an exponential function is one that may be written in the form either y or f of x equals, let's use y, equals a times b to the x power. In the future, we'll see there's another form, continuous exponential form, but that requires the use of Euler's number, and we'll get there. But for now, let's just start with this definition. So there are some requirements on the constants. A needs to be positive, and it represents the initial amount in any word problem. So you'll note that if you plug in 0 for x, then b to the 0 power is 1, and you'll just end up with a. That's why it's the 0 amount. So we can specify that a little more clearly. That is 0 comma a is the y-intercept. And b, which is the exponential growth, the exponential base, it has to be positive, and it also cannot be equal to 1. If it were equal to 1, then 1 to the x is just always 1, so that's not interesting. You would just end up with a constant function. So this is known as the exponential base. And this multiplicative growth can also be thought of as a fixed percentage change. So there's a way to translate from your exponential base to a percent growth or decay. So if we write b equals 1 plus r, r is said to be the percent growth or percent decay. It'll be growth if the percentage is positive, and decay if the percentage is negative. So we have quite a little bit of terminology there to introduce it. So let's see what that looks like in an actual example with some numbers. So in this example, let's say we have, we want to identify the y-intercept, the base, the exponential base, and percent change of each exponential function. So for this first one, a, let's say we have f of x, or you can think of that as y, is equal to 125 times 1.12 raised to the x. A lot of times with exponential functions, you will see them, very frequently they will involve time, so you'll often see t as an input variable rather than x. Okay, so just looking from the above things, again, if you plug in 0 for x, 125 is the guy in front, so your y-intercept is just 0 comma 125. Your exponential base is just the 1.12. So how do we figure out what the percent change is? So the percent change we would say, okay, well, 1.12, which is b, is equal to 1 plus r, and then we just solve this equation for r. So we would end up with 0.12 is equal to the value of r. So this means that f of x has 12% growth rate. You have to multiply by 100 to convert that decimal to the percentage. Okay, let's just look at one more of these where we're just identifying the parts of the function. So g of x is 2400 times 0.76 raised to the x. So again, the y-intercept here is just 0, 2400. Your exponential base is the 0.76, and the percent change this time will actually be negative, right? We have to set 0.76 equal to 1 plus r, and then when we subtract 1, we're going to end up with negative 0.24. So that's the value of r. So again, we could say g of x, when it's negative, it's a decay rate, not a growth rate. So g of x has a 24% decay rate. And when you use the word decay, it's just implying that that is going to be a negative value when you think about it in the function. Okay, so let's go ahead and think about, now we know what the formulas look like. Can we figure out what the graphs look like from those formulas? And we can. Anytime we have a function, usually what we can do is just plug in a bunch of points, graph them in the plane, and then see if we can connect the dots, forming some kind of pattern. So that, you know, a lot of times you just graph stuff on a calculator or a computer program, but occasionally it's good to do a few examples by hand just to make sure you can run through the operation if you have to. So let's make a table of values. Let's actually do it. And sketch a graph of just two of the, the kind of the most common ones you would think of. 2 to the x power, and let's say 1/2 to the x power. Pretty straightforward, but again, you might recognize the formulas but not exactly remember what the pictures look like. So what we want to do is just make a table. X, we can plug in whatever we want, and then 2 to the x is going to be our output or our y value. So let's plug in -3, -2, -1, 0, 1, 2, and 3. So 7 values there. So the first one, we would get 2 to the -3rd, which is 1/8, or 0.125 if you want a decimal. 2 to the -2nd, which is 1/4. 2 to the -1st, which is 1/2. 2 to the 0, which is 1. And then we just have 2, 4, and 8. So we have all of our values. Now we want to try and make our graph. I'm going to try and be as neat as possible, but that is the trouble with graphing by hand. You're never going to be as neat as the computer program. So I've got all my x values, so trying to keep everything to scale. Okay, so I don't know, why don't we start with the y-intercept, the one right in the middle. So we have a 1 that at 0, we're at 1, then at an x value of 1 we hit 2, 2 we hit 4, and at 3 we hit 8. And then we just keep having the distance to the x-axis as we go to the left. 1/2, 1/4, and 1/8. And we see those dots forming a clear pattern. So we see the the pattern is this smooth arc that goes up very quickly toward the end and just keeps getting closer and closer to the x-axis as we move to the left. Now what's going to happen when we do the 1/2 to the x? Well, you're going to quickly figure out that there is some relationship between the two functions. So again, let's plug in the same points. Well, if you do 1/2 to the negative third power, that is actually the same thing as 2 to the third power, which is 8. And the same thing goes for -2. That would give you 2 squared, which is 4. -1 would just be the reciprocal of 1/2, which is 2. Anything to the 0 power is 1, and then we get our 1/2, 1/4, and 1/8. So we get the same y values, but appearing in the reverse order that we saw previously. So if we draw this graph, you might try and guess how it's going to look. And if you thought that it's just going to be a flip about the y-axis, then you're exactly correct. So we have our values here. So at -3 we had the value of 8. At -2 we were at 4. -1 we were at 2. 1, 1/2, 1/4, and 1/8. I'm always a little bit worse at drawing the curve in this direction, being left-handed. Oh, yep, you can see already. It did not go well. It's a little bit tricky with this tablet I've got too, so let me see if I can. Oh, it's just hard for me to draw for some reason. It's hard for me to connect the dots in this way as a lefty. Alright, so that is as good as I'm going to do. Alright, so we get it. They should look like mirror images about the y-axis. So in general, for your exponential functions, as long as they are translated in any way, those two pictures, albeit they could be kind of stretched or shrunk, that's going to give you the general graphs of exponential functions. So the graphs of exponential functions. So let's just reiterate that is the formula y equals ab to the x. In the ones we just looked at, a was equal to 1 in both cases, and we had b equals 2 and b equals 1/2 to represent the example for growth and decay. So the graph of an exponential function has one of two possible shapes. As determined by looking at the exponential base. So on the one hand, we could have the growth example, where we have the x-axis as a horizontal asymptote and then it going to infinity. So this is growth. What does this correspond to? Well, either b is greater than 0, b is greater than 1, and anytime b is greater than 1, that means your percent change is also going to be positive. That's what indicates growth. And then on the other hand, you could have decay, where your x-axis is the asymptote to the right, and you go to infinity to the left. So this is decay. And this happens when, remember, b has to be positive, so b is either between 0 and 1, and that corresponds to values where r is less than 0. So here's a question for you to think about. So you might want to pause the videos on this one. But we've looked at some examples of functions so far, and we looked at how many points you would need to determine the graph of a linear function, which is just the graph of a line. And we've also looked at quadratic functions and other polynomials, and we see as polynomials get of higher degree, they require more things to figure out the precise equation. You're going to need more points to know exactly what the exact equation of the curve is. Well, how many do you think you would need to know the equation of an exponential function? So how many points, how many ordered pairs? So given that you know that what you're looking at is an exponential function already, how much more information do you need to find the equation? So how many points must be known to find the equation of an exponential function? Now, so pause your videos and think about that. You might think, so hopefully you've thought about it a second, but the shape looks more complicated than a linear function. So if you're thinking about the graph, you might say, oh, well, it seems like maybe I should need more than 2 because it's got that curvature to it. But on the other hand, if you think about the actual formula that we're working with, y equals ab to the x, well, how many things are constants and how many things are variables? Well, x and y are variables, so you have 2 variables and 2 constants. Well, for a linear function, you had the same sort of thing going on. Y equals mx plus b, y and x are the variables, 2 variables, and m and b are the constants, 2 constants. So it turns out that you only need 2 points. So just 2 points. Same as the minimum number for a linear function. You only need 2 points for a linear function. So let's go ahead and go through a couple of examples of actually finding the equation given that minimal information. So find the equation of the exponential function that passes through let's say 0, 100, and 2, 225. So this one is kind of the easier version of this problem, and the reason is I've given you one very particular point, which is the y-intercept. So note that 0, 100 is the y-intercept. So a is just the value 100. So we already know that our equation looks like y equals 100 times b to the x power. And we haven't used any of the information about the other point, 2, 225. So to find b, just plug in 2, 225 and solve. So we would have 225 is equal to 100 times b squared. And then we would have to divide by 100. So we'd end up with 2.25 is equal to b squared. And then from our history of studying quadratics, we know that b would have to be plus or minus the square root of 2.25. So b would have to be plus or minus 1.5. But remember, the definition of the exponential function requires that the base is positive. So in this case, only b equals 1.5 makes sense. So we end up with our answer, y equals 100 times our base of 1.5 raised to the x. And that is the equation that represents the exponential function that will pass through those 2 points. So that is pretty neat. Let's do one more. where we try to find the equation of the exponential function, but this time we don't have the y-intercept as one of those 2 points. So example, so find the equation, so same instructions here, of the exponential function that passes through (1, 400) and 4, 204.8. And I'm kind of picking these so that they come out nicely. In general, you could have a random set of points, and you might, if you try and take some root to find the value of b in your problem, you might end up with an irrational number or some decimal, where if you were doing things by hand, you might need to approximate. But okay, I just want you to see the nature of kind of how the computation goes. So for this one, we don't have the y-intercept. So the way I like to do it is plug each point into the formula that we have, y equals ab to the x. So we get 204.8 equals ab to the fourth, and 400 equals ab to the first. And I will tell you, the way I like to do it is I like to plug the one with the larger x value in first. So I plugged in 4 for x. That's the equation that's on top. If you do that, that'll usually save you a bit of a hassle, because what we're going to do now is we're going to take ratios of the equations. And when we do that, if you did it in the other order, you'll end up with a negative exponent. And if you just unnecessarily involve negatives, I've seen a lot of students make mistakes in those cases. So notice what we can do is we can make one equation out of these. If this system of equations is accurate, well, it will still be an equality if I take the same numerator and put it over the same denominator. So if I have 204.8 over 400, then I will have the same numerator and denominator if I put ab to the fourth over ab to the first. And then look what happens. Well, my a cancels out, so I'm just left with b to the 4 minus 1, which is b cubed, subtracting the exponents, and I just have one equation now with one unknown. So I get 0.512 equals b to the third, and I want to just raise both sides to the 1/3 power, and that will allow me to solve for b. So I have b is equal to 0.8. So now I know my equation looks like y equals a times 0.8 to the x. And now I can plug in either one of my 2 points to figure out the value of a. So let's plug in 1, 400. So 400 replaces y, and 1 replaces x. So then that's all we have to do to solve this equation is divide by 0.8. And we get 500 is the value of a. So we have y is equal to 500 times 0.8 to the x. And that is the equation in question. So I think we're going to stop here. That's a good introduction to exponential functions. And we'll pick up next time reviewing a bit and then comparing exponential data to linear data, and maybe also looking at some applications involving interest. So this is Dr. Lennon signing off.